This theorem is on open and closed sets in metric spaces. Let's first just remember a few definitions that will be useful. So if XD is a metric space and A is an element of the set X and R is a positive real number, then the open ball centered at A with radius R is the set below, the set of all elements of X such that the distance between A and X is less than R. A subset U of a metric space XD is an open set with respect to that metric if U is a union of these open balls as described above. And finally, a set C of a metric space is closed if its complement is open in that metric space. All right, so here is a theorem showing that the following statements are equivalent for a subset U of a metric space. So part 1, U is an open set as given by that definition above. Part 2, for any X in the set U, there is an open ball centered at X with radius epsilon sub X such that that open ball is completely contained in the set U. So these statements are equivalent. In other words, if this is true for every X in the set, then U is open. And if U is open, then that would be true for every X in the set. And third condition, this is in this certain case that U is not equal to the whole set X. So as long as this subset U is not equal to the whole set X, then for any X in U, the distance between X and the complement of U, X minus U, must be greater than 0. So, in other words, this is saying that for any U not equal to X, for any set U that's not equal to X, and for any X inside of U, the distance between the set X minus U, the complement, and the point X has to be positive. And so remember the definition of the distance between a point and a set, that it was the greatest lower bound of the distances between X and points that are in that set. So again, we're proving that this condition as well is equivalent to the other two. So if any one of these conditions hold, the other conditions hold as well. So let's prove this. We're first going to prove that A implies B. So let's let U be an open set, and we'll let X be an element of U. So we've got some open set. By definition of an open set, that means that U is a union of open balls in the metric space. So since U is open, that means that U is a union of open balls and in this metric space. And because X is an element of U, then there exists some A inside of U and some radius R greater than 0, such that X is an element of one of these open balls. And this open ball would be the ball centered at A with radius R. So U is a union of open balls. X is inside of it. X must be in one of those balls. We're just letting it be the ball centered at A with radius R without loss of generality. Okay, so here is our picture so far. I'm going to draw with circles. I mean, we know from looking at metric spaces that the open balls might really look like circles. They might look like squares or diamonds, for like say in the taxi cab metric on R2, or they might also look like these other weird things that we haven't even conceived of yet. So we don't know exactly what these open balls look like, but just this general, open ball that we're drawing right now is the ball centered at A with radius R. And X is an element of this open ball. What we want to show right now is that there is some epsilon greater than 0 such that the ball centered at X with radius epsilon is contained in this ball centered at A with radius R, because if we do that, then we know that this ball is contained in U, and that will prove that A implies B. So here's sort of a boring case. So if it turns out to be the case that the distance between x and A is 0, that means, by definition of a metric, that x and A are actually the same element. And in that case, then the ball of radius r centered at A is actually the same thing as the ball of radius r centered at x. And that would tell us that, of course, x must be in this ball centered at x of radius r, since r is greater than 0, which is contained in U, and then we would be done. So that's sort of a boring case, and we're just sort of eliminating it in order to assume that the distance between x and A is greater than 0. So otherwise, the distance between x and A would be greater than 0, so 0 would be less than the distance between x and A, which also must be less than r, by definition of the fact that this is since x is in the ball of radius r centered at A, and the definition of being in that ball is that the distance between x and A has to be less than r. Okay. So we can assume that that is true. And now we are going to define epsilon, the distance epsilon, or the real number epsilon, to be equal to r minus the distance between x and A divided by 2. So in other words, again, we're just drawing this ball of radius r centered at A. We have this point x somewhere inside of this ball, and we know that there's some non-negative distance, some positive distance between x and A, distance between x and A, and we are defining a new positive number epsilon to be r minus the distance between x and A over 2. That's our epsilon. That's the size of this now new ball centered at x. So now what we want to show is that the ball centered at x of radius epsilon is contained inside of the ball centered at A of radius r, which of course is contained inside of U. We know this already. And so again, that would prove what we need to prove. Now, if we want to show that one set is a subset of another, then we need to take an arbitrary element, let's say y, in that open ball. So here's some point y somewhere in there. And we need to show that y is also an element of the ball centered at A of radius r. So in other words, we want to show that the distance between y and A is less than r. And if we're able to do that, we will have proven this A implies B. So let's let y be an element of this ball centered at x of radius epsilon. Again, we want to show something about the distance between y and A. So let's consider the distance between y and A. Now that is going to be less than or equal to the distance between y and x plus the distance between x and A. Why is that? That's by the triangle inequality, one of the 3 properties of being a metric. So, okay, now this is going to be strictly less than. So here's the maximum distance between y and x, because y is inside of this ball of radius epsilon centered at x. So it's going to be less than this distance. We're going to be even super safe by saying it's less than r minus the distance between x and A. Because that is clearly true. It's less than that over 2, so it's definitely less than that. Plus, now we're going to leave this part unchanged, the distance between x and A. And so now we've got minus this, plus this, those cancel out. And so what we have shown is that the distance between y and A is less than r, which implies that, yes, y is an element of this ball centered at A of radius r, and therefore the ball centered at x of radius epsilon is completely contained in the ball centered at A of radius r, which is one of the balls that's in the union of open sets that comprise the set U. And so, yes, for any x in the set U, there is a positive distance epsilon such that the ball centered at x of radius epsilon is contained in the set U. So we have shown that A implies B. And I just want to note that this style of proof that we just did to prove that A implies B is a really common technique, a really common style of proof that we're going to see in this course. So we're going to see pictures that look like that pretty often when we're doing these proofs. Okay, so let's now prove that B implies A. So let's prove that. And we're going to assume that B is true, so we're going to do a direct proof. Assuming that B is true, that means then that for all x in the set U, there is some epsilon sub x greater than 0, such that the ball centered at x of radius epsilon sub x is contained in the set U. We want to show that U is open. So note then that the union of open balls for all x in the set U, the ball around x of radius epsilon sub x, well, every single one of them is a subset of U, and so therefore the entire union must also be a subset of U. So the union of all those open balls is a subset of U. And not only that, but the reverse inclusion is also true, that U is a subset of the union from x over x equals U of the open ball centered at x with radius epsilon sub x. Why is U a subset of that? Well, it contains every x in U. So for any x in U, clearly the union of these open balls, x sub centered at x with radius epsilon, for x in U, for any x in U, well, the ball clearly contains x because epsilon sub x is a positive radius. And so we have that the first set contains the second set contains the first, and therefore those two sets are equal. So that means that U is equal to the union for x in U of the balls centered at x with radius epsilon sub x, which is a union of open balls, a union of open balls in this metric space, and therefore, by definition, U is an open set. So that's B implies A. Let's now prove that B implies C. So let's suppose that U is a subset of X, the set X, and U is not equal to the entire set X, and that B holds about U. So this property is true about this set U. And we're, of course, trying to show that C holds. So let's let X be an element of the set U, and then we know that then there exists some epsilon sub x greater than 0 such that the ball centered at x of radius epsilon sub x is contained in U, so we know that from B. And what we want to show is this. We want to show that the distance between x and U complement is greater than 0. Remember, the definition of the distance between a point and a set is the greatest lower bound of the distances between that point and elements and other points in that set, such that y is an element of that set, U complement, so x minus U or U complement. We want to show that that greatest lower bound is strictly larger than 0. So in order to show that, let's let y be an arbitrary element of U complement. Then the distance between x and y must be greater than epsilon sub x. How do we know that? We know that because otherwise, if the distance was not greater, must be greater than or equal to, actually. We know that it must be greater than or equal to. Otherwise, the distance between these 2 points would be less than epsilon, and that would imply that y was in the open ball, centered at x of radius epsilon sub x, which is contained in u. But y is in u complement, not in u, and therefore that means that the distance between x and y is greater than or equal to epsilon sub x for all y in u complement. And that means that epsilon sub x is a lower bound for this set, the distance between x and y, such that y is an element of u complement. And because it's a lower bound, that means, therefore, the greatest lower bound for this set, distance between x and y, such that y is an element of u complement, is greater than or equal to epsilon sub x. If that's a lower bound, then the greatest lower bound must be greater than or equal to it, and then that is greater than 0, and so we have finished the proof that B implies C. Let's now prove that C implies B. So again, with a direct proof, let's suppose C is true. Let's let U be a particular subset of X that is not equal to the set X, and let the element X be an element of the set U. Then, by C, that means that the distance between the point X and the set U complement is greater than 0. Since it's greater than 0, we can just say it's some particular, we can call it some number, say that the distance between X and this set U complement is equal to some epsilon sub X, which again is greater than 0. All right, so now we want to show B. In other words, we want to show that the ball centered at X with this particular radius we've just given is contained in the set U. So to show that, let's let Z be an element of this ball centered at X with radius epsilon, and we want to show that any arbitrary element of this ball, Z, is also contained in U. So observe that Z cannot be in U complement because since Z in U complement implies that the distance between X and Z is greater than or equal to epsilon. Why is that? That was what we were assuming from C. So we were assuming that the distance between X and U complement was epsilon sub X. That's the greatest lower bound of the distances between elements in U complement and X. So that means that Z cannot be in U complement, and if Z is not in U complement, therefore Z must be an element of U, and so we've shown that any arbitrary element of this open ball is also an element of U, and so therefore we've shown that the ball centered at X with radius epsilon sub X is contained in U. So that's exactly what we wanted to show. Note that part C mandates that U is not equal to the entire set X. So just note quickly that if U was equal to X, then B would be immediately true because, the ball centered at X with radius whatever has got to be a subset of X. X is the entire metric space. X is the entire universe. There's nowhere else for that ball to be. So we have shown that A is true if and only if B is true, and B is true if and only if C is true. And by transitivity of logical equivalence, that means that A is true if and only if C is true. So you finally proved that theorem. That was a long one. Here's another theorem about open subsets of a metric space. So first, X, the entire set X and the empty set will always be open sets, and we already proved this in the previous video. Second, the union of any family of open sets will be an open set. And third, the intersection of any finite family of open sets is an open set. So now let's prove 2 and 3. So for part 2, the union of any family of open sets is open. This is essentially just by definition. Let's let the collection U sub alpha, and alpha can be over any index set. It might be finite, countably infinite, or uncountably infinite. So let's let this be a collection of open sets. Now, because each of these is open, that means each of these by definition is a union of open balls. So each U sub alpha is a union of open balls in the metric space. That's the definition of being an open set. And therefore, if we just take a union of a bunch of unions of open balls, that is still a much larger union of open balls. So the union U alpha is therefore a large union of open balls in this metric space and is open by definition. Okay, now let's look at proving that 3 is true. So we want to prove that any finite family of open sets is open. So let's let the collection UI from I equals 1 to n, now that's finite, I equals 1 through n, be a collection of open sets. Now we're going to look at the intersection. If it's the case that the intersection from I equals 1 to n of the UI is the empty set, then we're done. We already proved in the previous video that the empty set is always open. So otherwise, if it's not empty, then it must contain some element, and let's let x be an element of that intersection from I equals 1 up through n. So we're actually going to use the previous theorem, the part B of the previous theorem, twice. So in this proof, first by part B of previous theorem, that was the one that said that if a set U is open if and only if for any x in U, there is some open ball of radius epsilon, can depend on x, such that the open ball is completely contained in U. So we're going to use this part B of the previous theorem sort of twice. First, we're going to use it to say that because of this theorem, then for each I, for each set UI, because x is in that intersection of the UIs, that means that there exists some epsilon I greater than 0, it'll depend on which set we're talking about, such that the ball centered at x with radius epsilon I is completely contained in the set U sub I. So each set U sub I has such a property. So if this is U1, then here's epsilon 1, and if here's U2, then we're still talking about the same x, but we could have a different radius epsilon 2 around that x, and that ball is going to be completely contained in U2, and so on. Now we're going to let epsilon be the minimum of these epsilon I, these different radiuses from I equals 1 to n. So from 1 less than or equal to I, less than or equal to n. So out of all these different radiuses that we have from these different sets UI that are open, whatever is the minimum of these radiuses is going to be our epsilon. So let's note a couple things. Then the intersection from I equals 1 to n of these balls centered at x of radius epsilon I is just going to be the ball of radius x centered at this minimum epsilon, because we've got, again, these balls centered at x, different radiuses, and whatever is the smallest radius, that's going to be in the intersection of all of those balls. And further, this intersection, so what we have is that the ball centered at x of radius epsilon is equal to the intersection from I equals 1 to n of these balls centered at x with radius epsilon I, and the intersection of those must be contained in the intersection from I equals 1 to n of the ui, because each of these is contained in each of their corresponding ui's, and so the intersection of the ui's contains that entire set. So what have we shown? We have shown that for any x in the intersection of the ui's, there is some epsilon greater than 0, such that the ball centered at x of radius epsilon is contained in the intersection of these ui's, I equals 1 to n, and by 3, again from that previous, by part B of that previous theorem, because there's this ball centered at any point x of radius epsilon, depending on x, contained inside that set, that tells us that that set is open. So by part B of that previous theorem, the intersection from I equals 1 to ui to n of the ui's is an open set. All right, so that is the end of this proof. One thing I'd just like to note quickly is that, we proved that arbitrary unions of open sets are open and finite intersections of open sets are open. So this is just a note that arbitrary intersections of open sets are not necessarily open. So let's see this through an example. Let's do just the real numbers with the usual metric. And we already saw that open intervals, intervals that we normally think of as open, intervals A, B, not including their endpoints, are open in R with the usual metric. So negative 1 over n to positive 1 over n is open for all n in the natural numbers in this metric. Now let's look at the intersection from I equals 1 through n, or 1 through infinity, of the intersection from n equals 1 through infinity of negative 1 over n to positive 1 over n. What is this intersection? So can any positive number be in it? No, because there's some 1 over n such that 1 over n is less than that positive number. Similarly, no negative number can be in it. The only thing in this intersection is the element 0. So 0 is the only thing in that set. And this set is not open in the usual metric space for R. How do I know that it's not open? If we let epsilon be greater than 0, or for any epsilon greater than 0, the ball centered at 0 of radius epsilon cannot be contained in the set containing just 0. And again, really we're employing B of that previous theorem again, that a set is open if and only if for any element in the set there is some ball of positive radius centered at that point, completely contained in the set. So because that is not true for any epsilon greater than 0, that means that the set containing just 0 is not open. So we see that arbitrary intersections of open sets are not necessarily open. This is a countably infinite intersection of open sets. So we have a corresponding theorem for closed sets in metric spaces. So we've already seen that the entire set X and the empty set are closed sets. And for the other two parts of this theorem, these are going to be homework, but they're not too bad. So you're going to base it on two things. So you're going to base it based on the previous theorem, the definition of closed sets, which is that a set is closed if and only if its complement is open, and then also De Morgan's laws. So De Morgan's laws is something that we saw in proof. We saw it both for logic and for sets. So you'd be like most familiar in this context with, say, the complement of A intersect B is equal to A complement union B complement, and the complement of A union B is equal to A complement intersect B complement. Now, this is also true for arbitrary unions and intersections. In other words, the union over any index set alpha of A alphas complemented, we could do with a C or a line over top, either way, is going to be equal to the intersection over alpha of each A alpha complemented individually, and similarly, the intersection of the A alphas complemented over alpha is going to be equal to the union of each A alpha complemented individually. So this is theorem 1.6 in our book. So it's in sort of the preliminaries chapter. So you may or may not have seen this proof in our proof sequence for arbitrary unions and intersections, but it's essentially the same proof. I'm just going to do the proof of this one really quickly just to illustrate that, yes, this is not a stretch. So let's let X be an element of the union of the A alphas and then complemented. What does that mean? Then X is not in the union of the A alphas. So if it's not in the union of them, that means that X is not in A alpha for any alpha. Therefore, for each alpha, X is in the complement. If it's not in the set, then it's in its complement. And so X is in every single one of those ones. Therefore, it's in the intersection of the complements. Now let's do the reverse inclusion. So let X be an arbitrary element of the intersection over alpha of the A alpha complements. That means then that X is in A alpha complement for all alpha. So if it's in the intersection of all the sets, it must be in each set. And so that means that X is not in A alpha for all or for each alpha. And that tells us then that, therefore, if it's not in any of the alphas, that means that it's also not in the union of the alphas. So X is not an element of the union of the A alphas. And because it's not in the union of the A alphas, that means that so X is in the complement of this set. If it's not in that set, then it's in its complement, and we are done. We've shown that the intersection of the complements is contained in the complement of the unions, and vice versa. Therefore, these two sets are equal. And the other of De Morgan's laws also works for arbitrary unions and intersections. So using those, each of those pieces, the definition of a closed set, the theorem above, and De Morgan's laws for arbitrary unions and intersections, you can do those two homework problems.